Have you ever mixed two things together, maybe in a lab beaker or even just a cup at home, and been totally shocked by how hot it gets? I mean, it seriously feels like you're creating heat out of thin air, like some kind of magic trick. But you know what? It's not magic. It's all about hidden energy being released, and today we're going to pull back the curtain and see exactly where it comes from and how engineers manage to control it.
So let's start our investigation with a really simple, hands-on question, one you might have even bumped into in a science class.
Seriously, think about it for a second. You take two substances, both at room temperature, you mix them together, and then bam! The container is suddenly way too hot to touch. Where in the world did that heat come from? It really does seem like it just appeared out of nowhere.
And this is a very real and sometimes very powerful phenomenon. I'm talking about classic examples like when you carefully mix concentrated sulfuric acid with water, or when you dissolve solid sodium hydroxide, that's NaOH, in water. In both of those cases, the temperature doesn't just get a little warm, it can absolutely skyrocket, sometimes even to the boiling point.
That heat you feel, it isn't some kind of trick. It's actually the release of energy that was stored away, hidden deep inside the chemical bonds of the stuff you started with. We're just making that hidden energy, well, in this case, feelable.
Okay, to really wrap our heads around this, we've got to zoom way in, down to the molecular level. Because what's actually happening is this incredibly energetic dance of molecules, breaking apart and then reforming.
Now, in science speak, this whole thing is called the enthalpy of mixing. I know, enthalpy sounds like a super complicated word, right? But it's just a precise way of talking about the total heat energy inside a system. So, the enthalpy of mixing is just the change in that total energy when you combine things, and that change is what we feel as heat.
So here's the absolute crucial point. Every single chemical mixture is like an energy transaction. First, you have to spend some energy to break the bonds that are holding the original molecules together. You can think of that as the cost of the reaction. But then, when new, more stable bonds form in the solution, energy gets released, and that's the payoff.
And this is it. This is the key to the whole mystery. The mixture gets hot when that energy payoff from forming new bonds is bigger than the energy cost of breaking the old ones. You've basically turned an energy profit, and all that extra energy has to go somewhere. So it escapes into the mixture as heat. Simple as that.
Okay, so if this is all about energy costs and payoffs, how do scientists and engineers actually keep score, right? How do they predict if a mixture is going to turn a profit and heat up, or take a loss and cool down, and by how much?
Well, they definitely don't guess. They use a really methodical and powerful framework called an energy balance. And you should think of it less like a crazy science experiment and more like accounting.
All right, I know this equation might look a little intimidating at first glance, but I promise you, the idea behind it is incredibly simple. It's just like balancing a bank account. You've got energy coming in, those are your deposits. You've got energy going out, those are your withdrawals. And then you have energy being generated on the inside. That's your interest, or in our case, the heat from our reaction. An energy balance is just the tool that makes sure it all adds up perfectly.
The whole process is super logical. First, you just map out all your deposits and withdrawals, so all the materials going in and out. Second, you look up the exact value of each of those transactions. That's the specific energy, that enthalpy, that each part carries. And finally, you just solve the balance to find your net profit or loss, which is the final energy change that tells you if things are about to get hot.
But to do all this energy accounting, where do engineers even get the numbers? I mean, they're not just pulling them out of thin air. They've got a whole toolkit of resources to get the exact data they need.
Yeah, this is a really precise science. We're talking decades of careful experiments that have produced these incredibly detailed tables and charts. They basically act like official bank statements for chemical energy, giving engineers the exact values for countless mixtures.
So for example, a data table like this one is an absolute goldmine. If an engineer needs to know the exact heat of solution, which is pretty much the energy bonus you get when you dissolve something like sodium hydroxide in water, they can just look it up right here. It gives them the precise value they need for their energy balance. Zero guesswork involved.
And it's not just about simple tables. They also use these powerful visual tools like this enthalpy concentration chart. I want you to think of this as a stock market chart, but for energy. An engineer can use this to see instantly how the energy of, say, a sulfuric acid solution changes as it gets more concentrated, or as its temperature goes up or down. It's like having the entire energy landscape right there on a single page.
Okay, so this is a really cool way for chemists and engineers to track energy. But why should the rest of us care? Well, it turns out that managing this hidden energy is not just some academic exercise. It has massive real-world consequences.
You know, mastering these energy balances is absolutely critical for our safety and for progress. This knowledge lets engineers design huge chemical plants that won't have dangerous, runaway temperature spikes. It's the key to making industrial processes way more energy efficient, which saves a ton of money and resources. And it gives scientists the incredible precision they need to control reactions, to invent new medicines, and develop new materials. Honestly, mastering this hidden energy is what makes so much of our modern world possible.
So, the next time you use one of those self-heating hand warmers, or even just dissolve a spoonful of sugar in your coffee, just take a second. Think about that silent, invisible energy transaction that's taking place. Bonds breaking, new bonds forming. It really leaves you with a final thought. What other hidden energy transformations are powering the world all around you, right at this very moment?